Hello, I'm David Shin and this is Lab 5 and I analyzed the motion of a falling slinky. So the purpose of this lab was to analyze the two-dimensional motion of dropping a slinky from its equilibrium position, which is at rest. We then take the analyzed model and generate a computational model to compare the two. This experiment utilizes concepts of energy and forces during the motion of the slinky falling. I gathered the physical data in Tracker and used GlowScript to generate a model. The object uses a spring. Again, the concept used in this lab are energy principles, which are not used in the model, and Newton's second law. Here are some equations and concepts. Newton's second law states that net force is equal to change in momentum divided by change in time. And here we have the two forces in the system, force gravity and force spring. And then we can use these two forces to calculate the forces acting on the slinky at different points in time in the video. Before the slinky is dropped, the force of the hand holding it up ensures that it doesn't fall. And since the slinky falls with increasing speed, there is acceleration, meaning there is a net force. It's important to note that the acceleration is not constant due to the force of the spring, so it's not just force of gravity, and the net force changes as well in different areas of the video. So I just assumed that F net was just force gravity in my model, but I also did not account for drag force. And the model generated was using a line of best fit from the data in GlowScript, and we found that the measured position change wasn't exactly linear. So here's just a quick demo of how the data looks. And the previous equations and modeling can be used as there's only motion in the y direction, meaning that there is no regular motion, and the slinky follows the normal conditions of an object being acted on by a force. The system is a slinky with the surroundings being everything else, and the initial positions are 0.33 for time and negative 0.226 for y in meters, and the slinky starts at rest. And so I get the data using GlowScript, and the spring force affects the force of gravity as the slinky doesn't drop down uniformly like a ball, and I measured from the top of the slinky. And this top of the slinky affects the motion of the whole slinky. As you can see in the video, the whole object waits for the top to gather in like a ball before it starts moving again. And in terms of the GlowScript code, I used Lab 1 starter code, but I just modified it. And I also had the only force in GlowScript being the force of gravity, as tension force becomes 0 as the slinky is dropped, and calculating spring force would be too tedious as the S difference at each data point. So here are my tracker graphs and data. You can see here, as I was talking about before, this is where the top of the slinky meets the bottom, sort of, and it acts more like not really like a pendulum, but you can see that it meets and it waits, and then it pushes the bottom forward. So that's that irregular change in data. Here's just the data of the slinky collected, and the average slope from this point to this point is negative 2.5078 meters. And here's my GlowScript code. As you can see, I initialized it with the ball being 0.5 kilograms. This is the time step, gravity. And here are the forces. You can see that F net, I only accounted for force gravity. You can see the difference in the graphs here. So this is the motion of the GlowScript data. They do have very similar overall slope, which is this being negative 2.2638. But you can see that this motion of position differs drastically from this motion of position, as this motion only accounts for the linear acceleration, while the other one has this force spring affecting the force of gravity, meaning that it moves regularly, especially around this point in time, moving that it wouldn't move in a parabolic decreasing motion. And this is just the velocity graph, again, to show that acceleration is uniform, unlike the actual position data. So like before, the GlowScript shows a parabolic decrease, and the real model shows more of a linear decrease. And this is largely due to the fact that I did not account for the spring force in my model on GlowScript. And as I said before, the average slopes are similar, but the net force of gravity is slowed down in the real model, unlike the computational model. And so some sources of error, the lack of spring force in the GlowScript model was probably the largest error in my lab, affecting the net force the most and affecting the motion the most, as the net force was probably a large portion of how the slinky moved, but it would be incredibly hard to calculate as the S's differ per each time indice. In addition, there are probably slight errors in tracking the data points. The blue circle position that I highlighted before wasn't due to error, but some errors, as in the Y could have been 0.01, 0.05 off, just due to clicking the top of the slinky slightly off. And so what does it mean? As you can see in the graph, this is the blue position where the slinky moves irregularly due to how the slinky is shaped, and this is attributed to the fact that the slinky is not a ball, and it moves irregularly due to tension and spring force within the system, or the internal energy. And finally, what if the slinky was dropped sideways? The spring force in the system would probably have very little effect, as it wouldn't be affected by gravity, and it would just move in the manner that a normal ball would. Like, the coils wouldn't be acted on by gravity, it'd just be sideways, and the greatest force slowing it down would be the drag force, but there would be no excess in internal spring force causing it to move irregularly. Thank you!